for the final lecture on renormalization, we have Martens talking, but I guess I'm introducing you now, but I guess you should probably wait till Dennis comes. So. Or if you want to start, he probably knows the beginning. So.
Okay, so we are going to speak about universality and rigidity in higher dimensions, low dimensions, like 2 dimensions, which is already very high compared to 1 dimension. Let's recall renormalization in 1 dimension. That's a pure doubling renormalization. So we have a unimodal map. Let's think about it as smooth and the tip behaves quadratic. And then we say such a map is renormalizable if it exchanges 2 intervals. Critical point somewhere here. And then you see that this interval is mapped into itself by the second iterate. And then you can rescale this interval and you get a new unimodal map. It is the renormalization of F. So Misha described extensively the hyperbolicity of this operator. Okay, so let's look at infinite renormalizable map. And so these are maps where you can repeat this process infinitely many times. And those maps, they are related to the transition from systems with entropy 0 to systems with positive entropy. And then what you see is that there is this first cycle of intervals which are exchanged. But then the renormalization which lives in this interval has again a cycle. And these 2 intervals are mapped inside here, and they are permuted. So we see a second cycle. And now you are again renormalizable, so there are 2 intervals which go around and you get the third cycle. And this converges, shrinks down to a Cantor set. Okay. So then something happens which is closely related to the hyperbola.
I just wanted to say, I don't know if Charles Spencer is still here, but one day in 1981 he came to me and said, Dennis, what? The Hausdorff dimension of the Cantor set changes if you change the critical exponent. And I said, you mean it doesn't change if you don't change the critical exponent? Because horseshoe Cantor sets are like butter. Their Hausdorff dimension changes like crazy. So here's a Cantor set whose Hausdorff dimension is some number.
And we'll describe
8 years later, anyway.
So let's describe a bit more the details of Dennis's remark about the dimension, the structure of this Cantor set. So what you can do is, so you can take like the big scale and you can look at this interval and then you can zoom down a bit and you can zoom down a bit more. And then if you look at this interval and you use your microscope, this is getting very tiny. So then you will see some big interval, and then on the next scale you will see two little intervals sitting inside. And they have a relative size within the bigger one. So these numbers are called the scaling ratios. And so if you would have like a middle third Cantor set, these two numbers would be a third on each scale and each interval. But in our context, the situation is a bit more complex. What happens is, if you look at the set of scaling ratios at the level, say, you go to the nth level and you collect all these ratios, and they are going to define the Hausdorff dimension of this limiting set. Then you can take the limit of that, and then let's call that the set of scaling ratios, asymptotic scaling ratios of this Cantor set. And then there is a theorem which is a direct consequence of the hyperbolicity of renormalization, which Misha described the other days. And the first theorem is, this is universality, that the set of scaling ratios is the same as a set of scaling ratios for the renormalization fixed point. And so in other words, the fine geometrical structure of the Cantor attractor of any of these infinite renormalizable maps is exactly the same as the scaling structure of the renormalization fixed point. Okay.
Well, that's like C9 and Hanin and the David Rands proved that. There are papers about that.
It's sort of, if you have to have,
No, so you have to have the fixed point.
you have to have the fixed point and the convergence.
Right, and then we can prove that.
That follows quite easily from.
Well, it's easy after it's proven.
No, of course, so.
The definition of an NP completeness.
So there's another
Right.
remark that this set is a Cantor set. And so our universal Cantor set at the limit of renormalization has everywhere different scaling ratios. So it is like not at all like the middle third Cantor set. It is a very rich Cantor set. And it is clearly not something you can make by hand. You need machinery to construct these fixed points. So this is universality.
Well, sometimes you don't know these scaling ratios. You know they exist, but you don't have a formula for them. Right?
So can you say again what a scaling ratio is?
Now you have this Cantor set, which is constructed like scale by scale. And then you look at one, so zoom out. So you see this one big interval, and then inside there you see two smaller ones.
Yeah.
And then you take the relative size of each of them in
Yeah, but that's not universal yet, right? Because that's not at a small scale.
No, so then you take like the limit when you go to deeper and deeper scales.
Of this finite set of numbers?
Yeah.
The set of all limits which arise?
Yeah.
So, I mean, I think isn't there a way to like take a point and trace its inverse orbit, and then that defines a dual Cantor set, and for each point in that dual Cantor set, there will be a well-defined number?
Yeah, exactly. That is like the scaling function. And this is, I didn't want to get
This is the image of the scaling
Exactly.
function.
Exactly.
Okay.
Exactly. Okay, so a closely related theorem to this universality is the rigidity theorem. If you take this Cantor set of our infinite renormalizable map, then that is actually conjugated to the Cantor set of the fixed point. And these Cantor sets are all adding machines over like the usual adding machine. And this conjugation is C1 plus a little bit more. And this reflects, except for the alpha, the fact that all the scaling ratios are the same. So these are almost the same theorems in one dimension. And we are going to look what happens with these two phenomena of rigidity and universality when you go to higher dimensions. So when Coulet and Precer and Feigenbaum studied this situation numerically, they introduced the renormalization operator, but they also conjectured that this universal geometry of this Cantor set is going to show up in higher dimensional systems, and even in fluid dynamics. And then after that, many experiments have been done, numerical and actual physical real-world experiments. And indeed, these numbers showed up. So there is something to be explained. Okay. So let me give let me say something about homoclinic bifurcation. So this infinite renormalizable situation was about the transition from entropy 0 to positive entropy. So topological change in the dynamics. So if you have higher dimensional systems, then changes in the topology of such systems are related to, not always, but very often, homoclinic tendencies. So what is that? So you have a saddle point with some contracting direction and some expanding direction. And then the unstable manifold sort of turns around and makes a tendency. So if you know, you could move up and a little bit down. And that bifurcation, of that perturbation, will change the topology in a dramatic way. If you move it up a little bit, you will gain some entropy. You will really create some new dynamics. and that creation of new orbits is done by Henon maps. So let me show you where they are. So you take a little box here. This is very important. And you start to iterate it. So because of the contractions it gets thin, and because of the expansion, it gets long. This is thin. And then eventually it will get somewhere. Oh, this isn't so nice. Something like it. And so now you can start to push this up. So you will see sort of like this horseshoe moving through the box. And then this perturbation up to coordinates can be given in the following. It's described by Henon. Because of tension, this is like a quadratic map.
So I was going to show Henon maps are all over the place.
They are exactly. They are all every bifurcation sort of. And these physicists and the people who do experiments, they see the Henon pictures all the time. So and that is related to this type of creation of stuff. So, so these return maps are Henon maps. So let me give a little bit more formal definition.
It's like an astrophysicist, right?
Yeah. So it's a map from the square to itself, and that is given by the formula of the formula. Something like this, where this little f is something unimodal, that it describes like the tangency. And then this epsilon is somewhat very tiny.
Oh, small.
Yeah. And the reason for this tiny is, so I have to add something, this has to be dissipative. So in nature there is friction. And that will imply that very often you see that the determinant, the derivative of a map, is smaller than 1. So then if you iterate a lot of times, you see that the determinant becomes very tiny. And the determinant is like this epsilon. And so these determinants related to homoclinic bifurcations are little perturbations of unimodal maps. So we are in a perfect situation that we are going to do some perturbative renormalization to it. Just for like the traditional and non-map.
So sorry, if the epsilon were 0, this would be a map of the square that maps it onto the graph.
Yeah. Let me make a picture. And so what you see is you take the square, but there is essentially no y dependence, so you squeeze it together to like the x-axis, and that x-axis is sort of curves according to this unimodal part, and then you fatten it a little bit. And that fattening is really something like this. It's like a little fattening of a unimodal map. And then there is this x here. It looks harmless, but it is going to help us a lot. This is really a normal form, and like with the coordinate things you really see this. But this x is going to help us a lot. And what this x is doing is, if you take a vertical line, then that vertical line is mapped to some horizontal line, and it is contracted a lot. Because the contraction is controlled by this epsilon. It's contracted a lot. So vertical lines are strongly contracted. That's you have to. So in the case, so the classical Hanon map is this one: is a minus x square minus y x. Okay. And if you go to the A and B plane, then for B is 0, there is, and we are essentially speaking about, or we are speaking about the unimodal map. And then there's somewhere here is this limit of periodology, which Misha spoke about the other days. And now we are going to move up a little bit, and we would like to understand what happens if you increase the epsilon or the part. Okay. Okay, so we are interested, so what you will see is that if you start to push this up, you will start to see this period-doubling cascade, which we have been discussing the other days. So we expect that renormalization is going to play a role here, if you push it through. So we are going to speak about, let's say, what is a renormalizable non-map. You take your, it's very similar to like the one-dimensional picture. So you have your map, and then there will be somewhere here a box, and this box is mapped to something, and then it is mapped. It's sort of, so this is renormalizable. And then what you do is, then the same scale, you rescale. And you get the renormalization of f. Now there's a little technical detail which we have to address now. So it's technical, sorry. So our maps, they have this property, vertical goes to horizontal. So if you would do this with an affine rescaling, you would not fall back in this class. So we do have to use here non-affine rescalings. And it looks very scary. But there is a unique, which diffeomorphism to choose is forced upon you. You don't have essentially no freedom to do this. But it is a diffeomorphism, not affine, and we will have to address that. We will come back to it. It will play an important role. Okay. So then let's go back to we are interested in this transition from the periodic cascade. So we have to look at infinite renormalizable maps.
This picture with homoclinic tangency, you could do that in any number of dimensions, right? As long as you have one direction this way, and infinitely as many as you want in this direction, or way. Yeah.
So this should be like one dimensional.
Right, and then you have a lot of contracting directions.
And so if you have a real world physics, it's one expanding.
One important variable.
One expanding the Lyapunov exponent, then you expect to see one-dimensional stuff going on. There is dynamics where you have two expanding directions, and then you are completely lost so far.
Multimodal.
Or multimodal might be okay, but I think the real next difficulty will be if you have more expansion. Okay, so we have our renormalization operator. This is important. This construction. So the first non-renormalization operator was introduced by Collet, Ekman, and Koch, where they extended the one-dimensional renormalization operator in an analytical sense, and we needed. So this is the Carvalho. We needed a renormalization operator which allows us to study the geometry. So this one we made to really attack the geometry of infinite renormalizable maps. So let's look at these infinite renormalizable maps. So we have F. We have a box, shape, and then we have scaling, box, and then we have scaling, this will continue like this, and then you have the same as in one dimension. You have two pieces flipping around. That is the first cycle. Then you have these two pieces here, they are sort of sitting here, so they are flipping around here. So that contains the second cycle. And this continues like this. And we will again shrink down to a couple set. Okay.
What's the dynamical meaning of that Cantor set? I mean, for Feigenbaum, it's a attractor, so.
In this case, it's exactly the same.
It's an attractor.
No. You asked it.
Let me answer the question. And so what happens is, you get this Cantor set. Almost every orbit will converge there. And the rest of the dynamics is sitting in periodic orbits of period 2 to the n. And that is it. It's like that from this perspective, it's exactly the same dynamics as the corresponding one-dimensional maps. It's exactly the same. There is a bit more topology because there is stable and unstable manifolds there intersecting in few ways. It's not really, but from a measured theoretical point of view, it's exactly the same.
But you're saying at the place where all the 2 to the n periods already exist. It's like if
you think of a one-dimensional situation, you have the period doubling, the dynamics is very simple. You have the next period doubling, it's very simple, and so on. In the limit is where you see, in the parameters where you see the Cantor set, and you're saying that's the same thing here, where you move A, and you were like, if you take your original hang-on family, and you fix B small, and if you just move A up, and you're cutting that line, it's at that line that you have this dynamical thing that sits for the map, right? An invariant set for the map.
Now, so there will be a little curve.
Right.
Some analytic curve.
Right.
Where you see this person that's sitting there. And I can describe you a little bit the dynamics. So there are these two boxes flipping around. And like in a one-dimensional situation, there is a fixed point between them. And then there's a stable manifold and things are running around them. And eventually they're pushed into these two boxes. And then the dynamics is described by this. Which then again is a period 2 point, and it lives somewhere inside here. And eventually everything will be mapped into these boxes. So this Cantor set attracts almost every orbit, except for points in the stable manifolds.
But the point is, these iterates, this picture that you have there, are not the same map. They're the rescaled map, right? You can ask the question about what the OF looks like for the original map. Right?
So this guy is what you see here. And so the inside here is some the Cantor set. Right. And on the first scale it has 2 boxes. But in each box there are 2 other boxes. These are traces of the renormalization.
Right.
And then inside there are traces of the
right. So you take those big ones, you scale back down and you stick them in the first box, right? Okay.
This is all in the domain of the original map. Yeah. And it is, let me write it down, it's a Cantor attractor. Okay, so let me begin with it's like the news you expect. Let me describe what you expect to happen.
So have they seen this in numerics?
Excuse me?
Have they seen this Cantor attractor in numerics with the scaling ratio? Or some kind of
No,
geometry?
you will come to that.
Okay, okay, sorry.
It will be. We will come to that. They will come too fast. Okay, so let me write down like the good news. Let me write down the good news. Now, the Hausdorff dimension of this thing is smaller than 1. It's like in the non-dimensional case. So then let's go to a bit more complicated thing. There is universality, just what we expect. And it looks like this. So there is something that actually plays a very important role. So this Cantor set is just an adding machine, and hence it has uniquely ergodic. Hence unique measure. And that is just, and you put like half of the mass here and half of the mass here. And then a quarter of the mass here, quarter of the mass. You just put on each piece equal mass. So that is a unique invariant measure. And then there is something that you call the average Jacobian, BF, which is e to the log of the Jacobian dmin. The average Jacobian. And this number is going to play a very important role. And let me describe you the first place where it shows up. And so this is still the same group of people, Algebraic value, Misha Lubitz, and myself. So what you see is if you look at the nth renormalization, it's supposed to converge to the fixed point. What you see, it is something like this. It is some unimodal part, which indeed converges exponentially to the one-dimensional fixed point, so it is the way it's supposed to be. And then there is this perturbation. And that will look very special. It will look like the Jacobian to the 2 to the n. Times some function, it's a universal function, like once and for all, times y times some exponential instead. Okay. So this should be
one piece converges to the fixed point, and then you have the average Jacobian times a universal function, okay, times the formula times, okay.
But look at this, is like it's like 2 to the n. So this is something super exponentially small. So this should be completely harmless. Okay, so then there's the other thing. Remember that all these scalings here, they're just diffeomorphisms. So it could be that if you look at our
So you must know bounded geometry by now, of Cantor set.
let's go there a little bit.
No, but if you can state this theorem, you must know bounded geometry. There's no geometry, there's no Cantor set in that statement.
No.
But to get that, you must know at least bounded
Let's,
geometry.
that has a more delicate answer to this question. I come back to that later. Okay? So we see this really expected convergence of renormalization, but we are interested, as Dennis pointed out, in the actual geometry of what is going on here. So we need to know how all these rescalings, which are diffeomorphisms, deform what is going on here. And it could be a completely crazy diffeomorphism. So it could be that this convergence of renormalization has nothing to do with the actual geometry of the Cantor set. So luckily that's not the case. So if you look at the long rescaling, so if you go from here down to there, then that also has a universal shape. And it looks something like, well, it looks like a matrix. This is a little tilt matrix. It tilts a little bit. And then there is something like sigma squared to the n, and something sigma to the n, 0, 0. And then here is some universal diffeomorphism. So the main chunk of the map is just some fixed universal diffeomorphism. So something we understand very well. And then there is this linear stuff. And exactly.
Fixed number.
Now, this is important. So the TF is proportional to the BF. So it's a very tiny tilt. And
Can you say again what that expression represents? What is psi sing? Psi, what? No.
You must know what the left-hand
What
side.
is it the formula for?
Composition of this size. Composition of this size 1, size 2, etc.
Ah, it's the rescaling map. Okay.
had a long rescaling map. But normally this is just an affine. In the one dimension this is just an affine map. But in our case it is some diffeomorphism.
And what's the domain of validity of this discussion?
A big ball around the square. You see two.
No, I mean, for example, does it work for any B sub f or?
No, all this is perturbative. So B has to be small enough.
Ah, okay.
This universal map extends to a definite disk around the unit interval. And this diffeomorphism in one variable also extends to some universal thing. You can if you take the unimodal fixed point apart, you can see this guy sitting inside there. So there's a strong relation between them.
Do you need some errors? This side on?
Yeah, there is something, some exponential error. And these scaling numbers, this is a scaling number from the Unimodal map. But what is important first is that it is one and the same number and that it is smaller than 1. With the little tail, it's proportional to the Jacobian. And this is what we're going to explore. Okay.
So already you have uncounted many models. There's a little
Oh,
b.
yeah, exactly.
Divided.
Yeah. And this little b is actually going to distinguish smooth flex.
Well, I mean, it follows from the statement.
Now, you know, it could be that.
No, it follows from the statement that you're saying, well, which ones occur? You're saying that sufficiently small ones occur?
All this stuff holds for okay, so now let's go to. So this looks all what you expect. It's a little delicate thing here. But now let's look at some numerical experiments. So there's another theorem, it is the same group of people, that there are two characteristic exponents. One is a neutral direction, sort of pointing along the counter set. So the invariant line field related to this is supposed to be the tangent lines to the counter set. And then there's another one which is describing the contracting part, and this is the law of B. And I would like to show you some pictures showing the line field corresponding to the neutral direction. So the experiment is done in the following way.
These are directions of the renormalization operator? What are they?
No, so we have the counter set, and there's an invariant measure there, and this measure has two Lyapunov exponents.
Oh.
And one gives you 0 and one gives you. So this is. So let me tell you what we are going to do. So take some piece in the nth cycle. And so at this point we have no idea how it looks like. But let's draw something. And this thing is floating around. And after 2 to the nth steps, it will be mapped inside. So there will be some periodic point. And this comes back.
So what?
A periodic point. And then, so that's one thing we know. But then inside this box, and there are two boxes of the next generation. And inside there we also have a periodic orbit of the next level. And then draw the line going through these two periodic points. And later we will see that this line is actually a very good approximation to the line field related to the neutral direction. It's sort of pointing along the counter set. The counter set is supposed to be somewhere. Okay, so let's make this. And for example, if you do this, if you do this in the case when B is 0, so when you have your map as a degenerate map, for example, at the fixed point, and then this counter set will lie somewhere here, and then this characteristic 0 direction are just going to be like tangent lines to this parabola. So the tangent lines at the counter set so it's a continuous line field, everything is perfect. So I would like to show you the picture. another button. We have to do. Oh, it's coming. Thanks a lot, sorry. Okay, so this is a picture in the degenerate case of the line field to the compensate. And you see that somewhere there is some compensate lying here. And you see the lines are nicely tangent, and there is some compensate here and here. And the lines, they nicely form an envelope of this parabola. So that was for we had our normal plane, and so this is for this. Now let's move up a little bit to B is a 10th, and then again we see this compensate, and let's see what happens with this line field. And then we get this. So you see, like what was very nicely smooth here, suddenly starts to unfold and wrap around. So what is happening there, initially all these pieces were nicely aligned, but suddenly there starts to be a lot of rotation. Like around, like where the tip is, it still looks much nicer. There's some turning here, but it looks much nicer. And this was for B, is a 10th. So let's go up a little bit.
The way of finding the position of the Cantor set, these lines show you how it's positioned.
Yeah. But also, so where it is, but also how the pieces are twisted. So if you go a little bit higher in B, so to B is 0.4, you see it starts to.
Can you point to the Cantor set in that picture, like where the?
Now there's some stuff here. There's some stuff here.
Now where are the first two big blocks?
Somewhere here,
Yeah.
and somewhere here.
Okay.
like something like this.
Yeah, right.
It's okay.
Okay.
But inside there's all this little stuff, and yeah. So this is for 0.4, and so we are already somewhere here. Let's move up. Okay. Let's move up. Yeah. Now 0.7 you can it really starts to wrap a lot. If you go to the almost conservative maps where B is 0.95, you see there is a lot of turning going on. And so this is very far from one-dimensional dynamics. But also notice that if you go only a little bit, this distortion happens already. So sorry. So this is for, at 0.1 you see it's already it's already doing this two-dimensional stuff.
So does the Cantor set lie on a fractal Jordan curve?
So it lies on a rectifiable curve. But I will describe your answer, the question more precisely. Because clearly it's not one-dimensional dynamics. There's something more going on. I can take this away. So let's give some theorems which describe the situation. The first one is actually perfect. So the first one, this is the same group of people. Het is Cantor set, dus not lie on a smooth C1. And related to this, the line fields related to this characteristic are not continuously. This line on rectifiable curve. Not a lot, but okay, so that is about. So let's come to. Remember, we were discussing universality and rigidity. So we saw already some universality. So let's see what happens with rigidity. And unfortunately, it's always the same group of people. Unfortunately, there is no rigidity. And the precise formulation is as follows. If you take two maps with different Jacobians, and you look at conjugation from the higher Jacobian down, that is at most C half 1 plus log B1 and in particular, if you would conjugate it with the one-dimensional Cantor set, and so where this Jacobian is 0, and this is at most C half. And so what you see happening that you have your one-dimensional situation, you move the arbitrary, where you have C1 plus Hilbert conjugation, that is the rigidity from one dimension. If you move it an arbitrary small amount up, then the C1 plus Hilbert conjugation immediately jumps to half. So you go immediately down to only Hilbert conjugation.
I would suggest you don't use this name for the theorem because you're sort of suggesting that in the other part of it there's like one or two parameters that might describe the geometry. So like it has finite moduli, which is you have a natural invariant, and then if you fix that invariant, then you might have some rigidity, right? Just like in climbing groups.
Yeah. So you know the conjecture is that if the B's are the same, if you have maps with the same B, then they are Hilbert conjugated.
Okay, well that's a lot of rigidity, right?
And that is true in the one-dimensional situation, and recently that also has been proved for the conservative maps. So if B is 1, and you have two of those guys, they are C1 plus Hilbert conjugated. In the conservative, like way up from here. So it might be that.
I'm not hearing all this. Say it again.
So the conjecture is that if you have two maps with the same average Jacobian, the B is the same, then the conjugation is C1 plus Hilbert. And that is true when the map has Jacobian 0. That's the one-dimensional theorem.
What? And if it's true, what?
If the Jacobian is 0, like in one-dimensional situation, that is true. That is, the conjugations are C1 plus Hilbert.
Here's the second part. There's a conjecture and then there's a statement or a corollary conjecture.
So let me try again. No?
It's very dumb.
Maybe I'll write it down. Conjunction. If B at 1 equals B at 2, then the conjugation from is C1 plus Hilbert.
In two variables.
Yeah.
This is the dumb conjecture.
And there is a theorem by Gaidachev, Johnson, and myself that if the B equals 1, so in the conservative case. And then you have C1 plus order rigidity. This is computer assisted, so it might be true that the conjugacy classes, the smooth classes, are controlled only by this Jacobian. But that is
But in this B equal to 1 case, you have what C1 conjugacy C1 plus alpha is on the whole system or on the...
no, only the Cantor, only because of
what's the guarantee of the Cantor center case? Because in your consideration, B is small, right?
Yeah, this is a theorem of a very different flavor.
So I guess, so is there an invariant Cantor set, first of all, in the conservative case?
Yeah, so there are maps where you have period doubling renormalization, and there is a Cantor set, and you can define the address.
It's just not in the tracking case.
Yeah. And there are elliptical islands around, and they might be responsible for this turning of these lines. So there might be, they are starting to influence them for B close to 1.
So in this theorem, you assume you have the whole Cantor set picture that you've been describing, but it's area preserving, and then you can have it. Okay.
Let me see.
Excuse me, one more question. This is one of my favorite problems is this, is to prove the period W universality for other exponents besides the quadratic one. So is this related to that in any way? Or is it just, I guess not, because it's really just quadratic?
It's a very,
okay.
this is really a Lanford type of, is behind this, so I do not really understand this. I'm a little bit slow. Equal to the conjugation.
No, I return to it because I learned that if you get some kind of flow and you have a homogeneous tangent, you then it behaves like the unimodal math where the power law is the ratio of two eigenvalues at the periodic point. So you could get a similar picture with the unimodal map with the general power law. That's a different story, I guess, right?
I think it is a fundamental question.
That's for flow. This is for discrete fashion. That's a flow in 3 space, though.
It's like the Lorentz flow and But let's stick to this. About the a priori bounds question. So we really so in Jeremy's talk yesterday, it was clear that a priori bounds is one of the core ingredients for one-dimensional renormalization. And unfortunately, in this Hanon context, things break down. That's a theory by Peter Hedlund, Misha, and myself. And the theorem goes like this: there is a set A in the interval, that's one defined once for all. And then if the average Jacobian is in this set, then no a priori bound. And what you will see is that in the one-dimensional picture, in a certain box, you will see. Oh, sorry, it's important. Oh, sorry, sir, I can prove that. Thanks. It might be the whole interval, we don't know that. But it is a condensed GL, full measure. So if you look, so what goes wrong is if you look at the piece in 1D, you have two little pieces which are sort of next to each other. Then in the 2D case, They will sort of become next to each other.
Fold.
Yeah, if you would like look at the line on 3, then this line would sort of become an S.
Oh, yes. Becomes an S. It's pointing in the same direction. It's still pointing in the same direction.
Let me say it more carefully. The ones we constructed to be bad look like this. But this is sort of the first generation of badness. If you go deeper, we lose completely control and the picture might be completely off the track.
I don't understand the statement. I mean, if you have universality, you have convergence to something, then you have compactness, so you have a priori bounds.
So it is not a priori bounds, but it is bounds on geometry of the counter set. That is what you.
What kind of bounds on the geometry?
No, so the statement is that if you take a piece, you take 2 pieces inside, then the distance between these pieces might be much smaller than the diameter of the pieces. Like what you see here, the distance between these pieces should be comparable to the scale you are looking, but in fact it is exponentially small compared to the diameter. And in one.
Aren't your rescaling maps stretching by very different amounts in 2 directions?
Yeah.
So they deflate that kind of effect.
It's more. This is a statement in the domain of the original map.
Yeah.
In this higher renormalizations, you are also going to see bad stuff, but that is happening much deeper. Okay, so and notice that it depends only on the value of the average Jacobian. But this is a set which is defined once and for all.
This last sentence you answered the first suggests that as you renormalize, you kind of straighten out the bigger scales of the camera set.
Yeah. And the little ones are still sitting there, and then you stretch these.
You should say that A is only, the measure is only the relative measure. It's only the small b.
Yeah, this is
like it's a set.
So everything has to be for small. Everything today is for small b. Like way out, you cannot say anything. Everything. That's what we put this on here, right?
Say 0 epsilon.
Thanks.
Well, I see that the universal example lies along the parabola.
Yeah.
So the big pieces of high renormalization have to lie along the parabola.
Yeah, exactly.
Okay.
Exactly.
So you're just saying that's all you can prove. Beneath that statement is chaos.
And this get bad. It is not only you cannot prove it, it does get bad.
And the geometric reason is the difference of Lyapunov exponents.
It has to, and also show you where the mesh comes from in the next. Okay, let me tell you right now. So is it going to waste the time? Okay. So if you allow, I would like to, instead of going in the technical details of it, I would like to describe the solution to this mess. So because what happened was, when we told this result to Feigenbaum, he said, I don't believe it, because the physicists, they measure all that, and this is there. But then he did actually a careful explanation.
Which result didn't he believe?
For example, this. That the geometry is really not a one-dimensional picture. So then he did a careful experiment, and he looked, say, at the end scale, where there are 2 to the n pieces, and n were bad. He actually found them. But n out of 2 to the n is almost nothing. So they are very difficult to detect, but they are there. And so that is the next. So let me describe what goes on here. So if you take a piece of the n cycle, so then there are 2 pieces inside. Let me draw one. Let me draw one here. Well, let me first describe the perfect situation. So in 1D, you can take a B in the nth cycle. Let's see where it is. Here we see the Unimodal map. Somewhere here you see our little piece. And now you can look under your microscope, and you will see a straight line. That is B, and then inside here there will be these two pieces at B0, B1 of the next scale. And these scaling ratios are coming from the renormalization fixed point. So this is the one-dimensional picture. So in 2D, you could do the same thing. You take your B in your cycle, and then so where our concept is lying somewhere here, and you take the same, the corresponding B, and then you can rescale it, and then there will be these two pieces. They are finitons. Then what you can do is you can try to approximate. You can put the box, the smallest rectangle box around them. Say this length L, and maybe this width will be times L, and you can cut off at the corresponding pieces, so you get the scaling ratio here, and you get the scaling ratio here. And then, what you would like to have is that this picture is close to this. So, S and epsilon, and this is the set of epsilon standard sticks. And what we mean by that is that the relative width is smaller than epsilon. And also, what we want is that these two scaling ratios are supposed to be what they are supposed to be. So, and then Feigenbaum's experiments show that most of them are like this. And the theorem goes like this. So universality goes, because we have bad stuff, but we replace it by another notion. So there is, and this is work with Misha, myself, and we call this probabilistic universality. It's going to be a probabilistic statement. And what it says is the following. There exists a number smaller than 1, such that the measure of the pieces on the nth cycle, which are exponentially close to what they are supposed to be, this is exponentially thin. This is larger than 1. It's exponentially close to, it's almost everything. And we couldn't prove that it is exactly n. Like the bad thing.
What?
Now Feigenbaum noticed that out of the 2 to the n pieces, n are bad.
Right.
And so we prove that
Right.
it's an exponential small fraction of these pieces which are bad. So they are difficult to detect. And related to this is the notion of probabilistic rigidity. It's a bit more technical to describe. But what you get out of that is that the Hausdorff dimension of the measure sitting on this compass set is universal. See?
So the measure of the measure
Of the
within
measure.
the Cantor set is universal.
Universal as BF changes or depending on BF?
Independent of B. Independent of B. And so
This state is independent of B. No,
This-
this state is independent.
this is independent. So there's a strong dependence of B inside the statement. So this set of good pieces, they are preserved by the conjugations. And they are also defined by so they are preserved by the conjugations if the maps have the same B. So there's a combinatorial language behind the construction of those pieces. And this description depends on the B. But it is sort of related to this theorem. There's a topological universality behind the set of good pieces.
So if I can just confirm your last point, so the dimension of the measure is always the same as it is for the Feigenbaum one-dimensional map?
Exactly. So, shall I write it down?
Yeah.
Statement.
0.5306.
Well, it isn't that 1.5.
Something. That is, you could call it probabilistic rigidity. It's a bigger statement, but what you get is that the Hausdorff dimension of the measure of your Cantor set equals the Hausdorff dimension of the measure of the
Equals 0.5306. 0.5306. I made that up. It's about right.
And so, just to finish, what happened is that universality and rigidity, which we see in one dimensions, does not survive in higher dimensions. But it can be replaced by,
You have to be smart to make it survive.
in the probabilistic sense, it survives.
Right. So what happens is intervals are going along, and just the one that goes through the washing machine gets tumbled out, and then the other ones go through nicely, and then something. Well, you probably have a picture of that. You must have.
I can make a picture which explains, but it might take a minute.
Well, let's applaud and we can ask.
Let's applaud.
Did you describe the picture you have of that?
So this goes back. Is it gone? Remember there was this universal, this long rescaling from the map to the renormalization. This is the long rescaling. And this rescaling had a universal shape. And essentially it looked like this. And there is this T, this is one BF, 0, 1. And then some universal division. But let's look at this. So this describes what happens with this box if you zoom down. So there will be somewhere here a little box. And using this linear part, we can describe how this box looks like. So we have the box of the renormalization with two nice pieces inside. And now we rescale. And then what we will see is there will be like a parallelogram. I made it a big. This is like sigma square to the n. And this comes from this part. And vertically, it is like sigma to the n. This is this part. And then there is this tilt. And so you see that this angle is like b. So now what you see is that there are these two pieces here which are nicely positioned in space.
Why is one box and one line?
Yeah, because remember that these NL maps, they contract vertically very strongly. And so
Oh, yeah, right.
it
Oh,
looks,
right,
it
right,
looks
right,
almost.
right.
And so, but then what happens with these two pieces, they are coming here, and they're sort of coming above each other. If we have this condition, then b times sigma to the n is sigma squared to the n. Whether if this angle times this really compensates for that. And so there is this condition that if you go to the right scale of renormalization, then these two boxes become almost above each other. But then we remember that there was this contraction.
Almost above each other. Above each other.
But then the map, you'll squeeze it together, and you will get. But you have to have this condition. And then you go to renormalization, where you can go deeper, and then you can repeat this construction to deeper and deeper scales, and you get this breaking down of a priori bounds on arbitrary small scales.
So only one out of the large number of pieces gets distorted somehow?
This is like the first generation of distortion. So there's a sequence of generations of where things are breaking up. And that is described by the number, by combinatorial properties of B. But what happens after the first destruction, I don't know. It becomes a mess.
Yeah, one more quick.
So for small b, you still have the same Hausdorff dimension as for the one-dimensional case. And if I understood it correctly, for area preserving maps, you always have the same Hausdorff dimension. Is it the same?
No.
You get
So
something
for the
different?
conservative, the geometry of the conservative map is very different from the dissipative map. And it's a different world. But somehow the technique from the one-dimensional survives there, using some computer stuff.
But that, he was asking, does that Cantor set have any bearing at all on the one-dimensional Cantor?
It's really a different
You
thing.
just know that it's something universal, but you don't know what it is.
Okay. Let's thank Martin.
So